This is topic 8.6, molecular structure of acids and bases. Today's objective, explain the relationship between the strength of an acid or base and the structure of the molecule or ion. So we're going to look at a bunch of molecular structures and from there interpret the strength of the acid or the base. So the strength of an acid or a base refers to the degree to which a Bronsted-Lowry acid or base dissociates in solution. So we're looking at donating protons and accepting protons. Who's more likely to donate versus accept? Strong acids and bases are considered to dissociate completely. So if it's considered a strong base, reminder that it is in group 1 and B of those metals like the potassium, calcium, strontium, etc. The stronger an acid is, the weaker its conjugate bases, and vice versa. So we talked about that before, just make sure you remember that. This is associated with a Ka or Kb, with those values, of an acid that is, or basis or acid that is greater than 1. So if you have a larger, the bigger the K or the Kb is, the more likely it is to dissociate. Therefore, it's a stronger acid because it's more likely to ionize. And therefore, the relationship is with that is a stronger acid, you get a weaker conjugate base. Kind of throwing this in there, but so we have perchloric acid, hydriodic, hydrobromic, hydrochloric, sulfuric, nitric acid. And they also say that chloric acid can be considered a strong acid as well. So here, just kind of read this here. The conjugate of a strong acid or base will have little to no properties acidic or basic or otherwise. So if you have a strong acid, your conjugate base is so weak that it doesn't have any real properties, so to speak. This happens because the anions are stabilized by one or more several factors. They may be very electronegative, and therefore they pull their electrons well, or they're stabilized for some reason, or the electrons are pulled towards a group elsewhere. So resonance is another key thing to increase stability and therefore reduce properties of the ion, of the anion, I'm sorry. If you have a weak acid or a weak base, they do not dissociate completely. Some examples include hydrofluoric acid or hypochlorous acid, or acetic acid, which is vinegar. They exist in equilibrium and they favor the reactants in this equilibrium. And bases such as ammonia, they are considered to be weak bases. Binary acids. The chemical structure of acids control their relative strength, bond length, bond strength, and electronegativities of atoms all play a role in how much a Bronsted-Lowry acid will dissociate in solution. So we have 4 different halides. So an halide is just a compound associated with a halogen, along with their pKa values. There's a general trend that acid strength increases for binary acids down a group of the periodic table. Hi is the strongest, while Hf is the weakest. So here, in this case, so the bond length and strength plays a great deal. So notice how the longer the bond is, the more likely it is to dissociate completely. So the shorter the bond, the greater the attraction, the less likely it is to ionize. So remember that atomic radius increases as you go down a family or group. So fluorine, chlorine, bromine, iodine. Iodine is the greatest, has a bond length, largest atomic radius. So it's more likely to dissociate. So therefore, the easier it is to dissociate, the stronger the acid is, which is kind of weird when you think about bond energy and being strong. It's kind of flipped in your head a little bit. So just remember for this, the easier it is to dissociate, the stronger the acid is. And look how the pK changes. So remember that if you have a negative peak, well, you have a negative pK here. So the trend shows you that the more negative it is, the easier it is for it to dissociate. So you may see a question at some point, possible, relating with Coulomb's law and all that type of stuff. So according to Coulomb's law, oxyacids. An oxyacid is a ternary made from three elements, acid, with one or more oxygen in its structure. So we have like hypochlorous acid, chloric acid, and perchloric acid. Generally, by adding more oxygen atoms, you're going to have a stronger acid, higher Ka, lower pK value. And this is because it's due to increased stability of your conjugate base. The more resonance you have, the more likely it is to want to stay in its ion form, meaning that the more likely it's going to want to dissociate into H plus and ClO4 minus, for example, because there's more resonance in this particular anion structure. So it's going to want to stay there. Adding more oxygens tends to increase the acid strength because there's an electronegativity. It's often referred to as a negative inductive effect. By drawing away the electron density from like the structure, by kind of displacing it, you're kind of displacing the strength over a greater area. Therefore, it's a stronger acid or stronger anion, and it wants to stay like that. So look from just comparing all of these anions. So you have hypochlorite, chlorite, chlorate, perchlorate. The more oxygens you have, the more likely, you notice, the more likely it is to create double bonds. Therefore, it's more stable, and there's more pi bonds, pi electrons being delocalized among atoms as you add more things attached to that central atom, essentially. In comparison to binary acids, ternary acids, the trend is a bit different. So by adding these halogens, Cl, Bri, you notice that electronegativity, remember that it decreases top to bottom down a group or a column. So by having chlorine versus bromine and iodine attached to it, there's a greater electronegativity. Because Cl is more electronegative than the others, it is more likely to give the HOCl, all of that together, is more likely to give up the hydrogen because there's kind of a drawing effect of the chlorine on the oxygen and the fluorine to kind of, excuse me, it has a stronger inductive effect. So therefore, it's kind of drawing the electron density away from the HO bond. Therefore, it's easier for it to kind of pop off. The more likely it is to pop off, the stronger the acid is. So make sure you kind of keep that in your head. The difference, how halogens kind of behave differently, or their effect is different based on the type of acid that it is. Similarly, well, I guess conversely. So if you have highly electronegative atoms on a base, they tend to make the base weaker. Electron withdrawal from the electron accepting component of the base's molecular structure. Carboxylic acids. So if you're going to go into med school, you're going to hear organic chemistry. You're going to see a lot of these type of structures that are kind of annoying. Not going to lie. So carboxylic acid. So it's a box of acids. So there's like a C, there's O's, I hear all that type of stuff. So another structure that can donate hydrogen, as you can kind of see, is called the carboxylic acid functional group. It consists of a carbon that is double bonded to an oxygen and single bonded to another oxygen. The second one is bonded to an acidic hydrogen. So this is the one that's going to be dissolved in water. You can kind of see that. This R group just is the remainder of the molecule. It's just something else that's kind of attached to. So you have different types of carboxylic acids, and the names are just based on what is attached to it, that R group. The double bonded oxygen has kind of the same inductive effect as we saw before, and so it draws electrons towards it and weakens this bond over here, more likely for it to pop off. So then this is called a carboxylate ion, and then there's resonance here, so now it's stabilized. So we have the nitrogenous bases of from DNA and RNA, all that type of stuff you saw in biology several years ago, I guess. So adenine, guanine, thymine, cytosine, uracil, you have these bases that have a lot of nitrogens on them. Some other examples include ammonia and CH3NH2. How do you account for the difference in pKa of acetic acid versus fluoroacetic acid? So just a reminder, the pKa is indicative of the strength of the acid. So the smaller the pKa value, means it's a stronger acid. That means that the lower value indicates the acid will dissociate more fully when it is in water. So why would fluoroacetic acid versus acetic acid be stronger? So again, talking about halogens, so this fluorine here, remember that fluorine is highly electronegative. Its presence withdraws or draws electrons from the rest of the molecule. This weakens the OH bond, making the proton more likely to dissociate, stabilizing the conjugate base. So nitrous acid has a weak acid, while nitric acid is a strong acid. Gives you the K and pK values. Why does nitric acid dissociate more completely than nitrous acid? Support your answer with Lewis dot structures. So, sorry, I think I forgot this. Where is it? Hold on. So a smaller Ka value means that HNO2 prefers to stay as an acid as opposed to dissociating. While nitric acid HNO3 has a Ka that's greater than 1, so it prefers to stay in its products. Why is that? We have to explain using Lewis dot structures. So we have to draw them out. So just HNO2, it has a total of 1, 5, and 2 sixes, so 18 electrons accounted for, while HNO3 has 1, 5, 6, 6, 6, so that's 24 electrons. So I will tell you that we're not really used to doing Lewis structures with not just a central atom, so kind of bear with me on this. So if we have, let's say, we have an H somewhere, so that's good. H has to be on the outside for both. So for both of these, so something you have to know. So nitrous acid and nitric acid, they both have some kind of nitrogen base anion. So that N would be in the center. And I will tell you that both of them are double bonded to an O over here. That means that the other nitrogen, so then on the other side of nitrogen, there is an oxygen here, and it's bound to a hydrogen. Here we have 2 more oxygens to account for, so it's very similar, but now we have to account for the third oxygen. So right now we have 2, 4, 6, 8 electrons here. We have 2, 4, 6, 8, 10 here. So similarly to other double bonded O's and all that, so over here we're going to have 2 lone pairs. So we have 2, 4, 6, 8, 10, 12. And then nitrogen has, let's throw on a lone pair for that one. So now it can kind of bond with, so now it has its lone pair, now it can bond with the other ones. So 2, 4, 6, 8, 10, 12, 14. The only place you can really put them is on the oxygens. Similarly over here, you have your nitrogen. And you have your 2 oxygens, or 3 oxygens, I'm sorry, and your hydrogen. So let's start by adding more. So we have 2, 4, 6, 8, 10, 12, 14. We have about 10 more to go. Wait, 2, 4, 6, 8, 10, 2, 4, 6, 8, 10, 12, 2, 4, 6, 8, 10, 12, 14. So let's put these on the electrons on the oxygen first. So this has 2 things attached to it, so we have 2 lone pairs. Over here, this has 1, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. They all have a full octet now, except for the H. Okay, so why would this happen? So I'm going to use a different color. So with this double bond here on the HNO2, this is one Lewis structure. You can actually have another one where the lone pair from here goes down here, and this one kind of forms like 3 lone pairs on the other oxygen. So it looks something like this. H, sorry, I was jumping ahead a little bit. So erase this, I apologize. So because now these are technically ions, there's a -1 charge on both of them. This is NO2 1 minus and NO3 1 minus. So by popping off this hydrogen here, I'm going to erase this one here. It still has its open electron, so to speak. We know that HNO2 has 18, but we lost we lost we lost the hydrogen. So see 2, 4, 6, 8, 10, 12, 14, 16, 18. So now that creates a formal charge of -1 on this oxygen, hence the -1 up here. Same thing, this hydrogen pops off. Knowing that we have both, so kind of following this pattern, we have the oxygen single bonded with 3 lone pairs. This is a -1 here, -1 here, and on this nitrogen, we actually have a +1 formal charge. So now that is still overall -1 charge. So looking at this at face value, we see that they're pretty much the same except for that extra oxygen. So why is there such a drastic difference in dissociation here? And to look at that and to understand that, we have to look at how the electrons are shared on these in these ions. Erase that. So this boils down to something called resonance. The more resonance you're able to display, the stronger the acid is. So the stronger the acid, the weaker its conjugate base. Here, the nitrate ion, we're going to see that it has a much weaker base, and that means that the nitrate ion is less likely to capture a free proton to reform the nitric acid. Here, nitrate, we see that is actually more stable. So we see the double bonds here. Anytime we see a double bond, we have to think that there is some p orbitals that are kind of overlapping, and these are going to form pi bonds. And in the pi bond, we're seeing that that's how you're able to see a pi bond, is referring to the double bond. So it happens both in the nitrate and the nitrite ions. So we can see that this can, on the, I want to use a different one. On the nitrite, you can actually change it to where it looks like this now. Where the double bonds kind of change position, so to speak. For the nitrate, you can see it can kind of go look a couple of different ways. So actually, let me try to do this. So you can see that nitrate actually has 3 different resonance structures compared to nitrite. So what we're looking at with a double bond is that it's delocalized pi bonds, amongst the whole ion, the whole molecule. So by drawing out 3 different Lewis dot structures, we're demonstrating different resonance structures for this. So in nitrate, we have pi electrons that are delocalized over 4 atoms as opposed to 3. And that makes it more stable, like we kind of talked about earlier in the lecture, which seems like a long time ago now I think about it, because this is a long video. Ultimately, this is why nitrate ion prefers to stay in ion, because it's more delocalized, more stable in the ion form compared to HNO2 or the nitrite ion, which kind of wants to be more stable in a sense. So in order for it to be more stable, it needs to accept the hydrogen in order to form back nitrous acid. All right, so if you have any questions, please let me know. Thanks.